So in the last lecture, we talked about the pulses with the hot Big Bang cosmology, and we discussed how inflation, which is a period of accelerated expansion, can resolve those pulses if it lasts long enough. Okay, so now today I'm going to talk about reheating, the end of inflation and the start of the hot phase, and also talk about the perturbations to explain how inflation is a theory for the cosmological perturbation, or how inflation explains the origin of cosmological perturbations. Okay, so we start from reheating. Oh. Reheating. Okay, so we talked about the slow roll inflation, which was realized by a scalar field rolling down a potential. And we saw that this potential needs to satisfy some conditions, which we call the slow roll conditions. So if those conditions are satisfied, then we saw that we can get equation of a state which is close to -1, and therefore we get an accelerated expansion. In fact, we get a nearly exponential expansion. Now, something that you can check is actually one of the homework problems, is that these slow roll conditions can be realized on a potential which is as simple as just the mass term m squared phi squared. So if I take v of phi to be just the mass term, then if the field is far enough, high enough on the potential, then the slow roll conditions are going to be satisfied. So you will see what is that high enough, what is the meaning of being high enough, far enough in the exercise. And let me also remind you why we wanted the rolling scalar field. We didn't want to sit at the bottom so we didn't want inflation happening at the bottom of the potential. We did not like this, but we liked this. So this was bad and this was good. And the reason is that we wanted to have something that plays the role of a clock, something that ends inflation. So in this case, when the field is stuck at the minimum, then at least classically it will always stay there, and then this we get basically a lambda dominated universe, which is going to be de Sitter, or asymptote to de Sitter metric, and it never ends. But what we really want is a period of inflation that ends and is followed by the hot phase of the universe that we observe. So this rolling scalar field plays that role. It acts like a clock that finally determines when inflation ends. So in this case, for instance, when this field arrives to the bottom of the potential, then the slow roll conditions are no longer satisfied. And that's the point when inflation ends. And then we can have transition to the hot phase. So this transition is called reheating, when inflation ends and then we want to go to the hot phase. It's called reheating. The re in the reheating is because I think in the past the founding fathers of inflation had this idea that, or at least some of them had the idea that the universe started from a hot phase, then went into the inflationary phase, and then again it reheats to a hot phase. So that's the re in reheating. That's, I think, the origin of the re in reheating. So let us study what happens in this simple model. So let's take V of phi to be m squared phi squared. And let us ask what happens at the bottom of the potential. So now the claim is that the equation of motion for phi is the same as before. So now we know m prime is just m squared phi. But the slow roll conditions are no longer satisfied if we are near the bottom of the potential. So we want to be in the regime when now the mass is larger than the Hubble parameter. So as you see, the potential, so if you remember, in the slow roll approximation, the Hubble parameter, or h squared, was determined by the potential. The potential would act like an approximate CC. As we go down the potential, then the energy density becomes smaller, and therefore the Hubble parameter becomes smaller. So at some point, Hubble parameter becomes smaller than M. So then of course we cannot neglect this term. In fact, the term that is small is this term compared to the other two terms. So what is the solution of this equation? When mass is big compared to the Hubble, the solution is an oscillating solution, whose amplitude is adiabatically changing with time because of this extra friction. So the form of the solution is phi of t equals to some amplitude a of t times cosine mt. And then if I plug this in the equation, what I'll find is that a dot over a is much smaller than m. It is given by minus 3 over 2 times h, which means that phi of t is equal to some constant divided by a to the 3/2 times cosine mt. And I'm ignoring some phase in this cosine. In principle, there is a phase. This cosine has a phase. Or we can choose the origin of t variable so that phase is absent. Okay, so now what does this imply? Well, let me here emphasize that this a dot over a is much less than a. In terms of absolute value, its absolute value is much less than. So what is the implication of this solution, this oscillating solution? We can, for instance, look at T00, which is the energy density, because that's the quantity that enters the Friedmann equation. So what is the energy density for the field? It is 1/2 phi dot squared plus V of phi, which is 1/2 m squared phi squared. Then under this assumption that A dot over A is much less than m, this rho is approximately or up to corrections which are suppressed by H over m. This is going to be, so from phi dot squared, I get m squared times sine squared divided by a cube. And here I get m squared times cosine squared divided by a cube. So the sum of the two becomes this prefactor c squared divided by c squared m squared divided by 2aq. Again, with corrections which are suppressed by h over n. Now, this is this should be familiar, this behavior of rho. It is the energy density of non-relativistic matter, right? It dilutes as 1 over aq. So that intuitively you can think about this oscillating field at the bottom of the potential as being a collection of these heavy, now heavy phi particles that are just sitting there and they are diluting with the expansion of the universe. So this is how raw matter would behave. So we go in a matter-dominated phase. So this is a matter-dominated phase. So remember, we started from an accelerated expansion. So here we are in the accelerated expansion when the Storrow conditions are satisfied. Now we go to a decelerated expansion, to a matter-like solution. Okay, at this moment, it's still not it's not exactly what we want, because we want to go in a hot phase when the standard model particles are in the thermal state. So this is still not exactly what we want, but at least we know that inflation has ended by this time. Now, in order to have the standard model particles to be excited to go in a thermal phase, we need to couple them to the inflaton. So we can consider some coupling to a standard model. For instance, some couplings like lambda phi squared Higgs squared. And now via this coupling, we can have inflaton particles going into Higgs particles. And assuming that this mass scale is much bigger than the mass of the Higgs, these Higgs particles are relativistic, they interact, and then they excite all other the standard model degrees of freedom. So the standard model goes into thermal equilibrium after a while. So this is called, this is one particular very simple example of reheating. Of course, I didn't work out the details to show that this is actually efficient and works, but there are concrete examples of reheating, in particular in M squared phi squared theory, which work, and one efficiently reheats and goes into a thermal phase. Okay, any question about reheating. If not, then we can talk about fluctuations. So let us remember the story that we had before about the fluctuations of some fluctuations on a FRW background. So we said that if we are on flat FRW, which is if not exact, it's an extremely good approximation here. We can decompose fluctuations in terms of momentum modes. And then those momenta, those co-moving momenta are conserved for remain constant. And then we had various regimes to consider. So what was important was the comparison between K, the co-moving momentum, and the co-moving Hubble scale, or the wavelengths, comparison between the wavelengths and the co-moving horizon. And that had a particular behavior. Of course, the co-moving wavelength is constant with time, just a number. But co-moving horizon has different behaviors depending on which phase of cosmology we are in. So if we are in the decelerated regime, when W is larger than -1/3, then the co-moving horizon, which is 1/h, is growing. While if we are in the accelerated phase, like inflation, W less than -1/3, then the co-moving horizon is shrinking with time. And then various K modes are just constant. So the so this given K mode corresponds to a co-moving wavelength, lambda equals 1/k, that is a constant. So we saw that what happens, or we name these different regimes. So here we say the mode is super horizon. And in the super horizon regime, we had, so for some simple example, like a mass speed, we had a growing mode and a decay mode, or a constant mode and a decay mode. And then here, when K is larger than H, then we are in the sub-horizon regime, when the modes oscillate, and we have wave-like solutions with amplitude that adiabatically changes with time. And okay, so we also saw that in the usual picture, in the hot Big Bang picture, we have modes which are super horizon that go sub-horizon, and we needed to somehow impose some initial condition for this super horizon mode. Now, for instance, we saw that if we consider adiabatic initial condition for the superhorizon modes with an amplitude which is a statistical variable with some Gaussian statistics with a particular power spectrum, particular K depends, then you get a nice agreement with the cosmological observations like CMB temperature anisotrope. But that was, at that level, that was something that we had to just postulate the initial condition for this superhorizon. On the other hand, during inflation, we have the opposite region. So we have early enough time, we have the modes are subhorizon and then they go superhorizon. And this gives us an opportunity to actually fix the initial condition under some reasonable assumptions without actually giving for every K mode, just postulating the answer. So how does it work? Let us think a bit about the physical scales. So physical wavelengths, which is the scale factor times the usual wavelengths, which is the scale factor divided by K, the co-moving. The scale factor times the co-moving wavelengths, which is the same as the scale factor divided by co-moving momentum. But perhaps there's a factor of 2 pi that I don't care much about here, because K is 2 pi over lambda, so yeah, maybe we can even put it here. All right, so now, so what happens to the physical scales with time? In an expanding universe, the physical sizes grow with time, or if we go back, the physical wavelengths shrink in time. Now we can compare that physical wavelengths with the curvature scale of the background. So we are on curved background. This expanding universe has some curvature. That curvature scale in FRW is basically determined by the Hubble scale. So that's essentially the only. Well, there is also H dot. So Hubble and H dot determine the curvature scale of the problem. Now, what happens in this region, in the decelerated expansion? Here, what happens is as we go back in time, the wavelengths becomes large compared to, even though the physical wavelength shrinks, the curvature scales shrink the curvature scale shrinks even faster. So the wavelengths become larger than curvature scale. On the other hand, during the accelerated expansion here, the physical wavelengths, if we compare it to the curvature scale, what is this comparison? This is basically our order of lambda physical times the Hubble parameter. In particular, during inflation, that's the scale of the curvature, just the Hubble parameter. Lambda physical times h, if we go back in time, it will go to 0. Why? Because h is approximately constant during inflation, but lambda physical is, so this is of order a, the scale factor, times h divided by k, which is the same thing as the co-moving or co-moving Hubble divided by k. And this goes to 0 as we go to let me say it this way. This goes to 0 at t goes to minus infinity during inflation, right? Because Here H is constant, K is constant. H is approximately constant, K is exactly constant, but A goes to 0 during inflation. Let me remind you that in particular, if we are in the slow roll regime and we ignore the slow roll correction, so H is approximately constant, which means that A is behaving like an exponential. So A is approximately e to the ht. So as we send t to minus infinity, then the scale factor goes to 0. So the physical size of our fluctuations becomes smaller and smaller compared to the curvature of the scale. In other words, so they are subhorizon. In other words, the frequency. So imagine if I have an observer who lives during inflation. This is the conformal time. And then during inflation, we have an observer. So conformal time is goes from minus infinity to 0 during inflation. And then near 0, we have a transition to the hot phase. So we are here. Here, as we go to earlier times, the wavelength goes to 0, which means that the physical frequency, omega physical, goes to infinity as t goes to minus infinity. While the curvature scale h is constant. So we are talking about fluctuations that are very high frequency compared to the curvatures. Now, there is a natural assumption that one can make at this point, which is that if we say we go to the beginning of inflation, so inflation, imagine it's long, it doesn't have to be infinite. We go to the beginning of inflation, then a natural assumption to make is that if there is an observer there, that observer measures fluctuations or excitations up to some maximum frequency. But we don't expect to have fluctuations at arbitrarily large frequency. This is just, essentially a common sense assumption. This is the thing that the assumption that we make, and we believe it's true in our everyday life. We don't expect we don't expect to have excitations at arbitrarily high energy. Why? Or arbitrarily high frequency. Why? Because that requires a lot of energy. So it's basically energy conservation that doesn't allow having excitations at arbitrarily large frequency. So the assumption to make is that fluctuations of phi k with k over a, which is omega, larger than some, let me call it k over ai. So ai will be, so this is t initial, beginning of inflation. K over ai larger than some omega max. These are not excited. Or in other words, they are in vacuum. They are in Minkowski, effectively, approximately in Minkowski vacuum, because we are at the scales much shorter than curvature scale. So we don't need to worry about the curvature and being on the curved background. We just put them in Minkowski vacuum the same way that at LHC we put everything on Minkowski vacuum unless we excite them. So they are in Minkowski vacuum, and then we evolve them in time. But once we make this assumption about the initial condition, then the evolution in time of this node is completely determined. And this choice is called, this choice for the initial state is called the Bunch-Davies vacuum. The idea that if when the modes go super UV, super subhorizon, then they should be in the Minkowski vacuum, except that they are adiabatically expand. And this uniquely fixes what happens later. So this, in particular, under this assumption, we now understand that the 1-point functions of the fields or these fluctuations will be 0, because we don't have any sources at those frequencies. The 2-point functions will not be 0, but these 2-point functions, they are not 0 because we are talking about a quantum field. And we have 0-point fluctuations of those quantum fields. So now what happens? What happens is that what inflation does for us is that it produces some super horizon fluctuations, because these modes are eventually going from subhorizon to super horizon, which are statistical, but this statistical nature of fluctuations is originated from their quantum mechanical nature. So we didn't have to have someone that produces some random variable here at the initial time. Just the quantum origin of these fluctuations makes them statistical variables. We can only talk about the correlation 2-point functions and have some expectation value for that. Okay, any questions so far? All right, if there's no question, then we can, I can tell you a little bit about the characteristic or qualitative behavior of this 2-point function. Of course, this is something that this problem is now fully well defined, right? If I write this scalar field on this background, then with this choice of the initial condition, we can just go and solve for the fluctuations and find the answer. It's a very nice calculation, but it's a little bit beyond the scope of the course. So I won't do that, but I'll tell you about some of the features of the result. I should also tell you that there is basically, since if we have a single field inflation, meaning that we have just one scalar field, then the way to proceed is that now we should consider both the scalar field fluctuations and metric fluctuations, and then to study this system together. So there will be Einstein equations and the field equation. This we should linearize this combined system, or take the full action and look at the quadratic fluctuations and quantize that. And there are some gauge symmetries that have to be fixed before doing this quantization. At the end of the day, there is a single scalar, real physical scalar degree of freedom in the problem, which will be the adiabatic fluctuations, which is related to the adiabatic fluctuations that we talked about before. Okay, so let us see some of the features of this correlation function, and then we'll be done. So I said that this 2-point function. So therefore, what I'm doing here is a little bit simplistic because I'm ignoring metric fluctuations. I'm just talking about this scalar thing. But they can be made more precise. So it's not completely fictitious what I'm showing. So if we look at this 2-point function, let's see how it would look like. And of course, these phi k's are functions of time also. So this is, I claim this looks like some function p of k and t, 2 pi q delta 3 of k plus k prime. Why? So why do I have this momentum conserving delta function? This just comes from the translational invariance of the background. So this just comes from the fact that I have we are solving this, calculating this on FRW background, and FRW background is invariant on the translation. Why does it only depend on the amplitude of the momentum? This is because of the isotropy of the background. So this is the result of rotational invariance, rotation symmetry. Okay, what else can we say? We have another symmetry, or approximate symmetry. So let us look again at the metric, and imagine I ignore the slow roll correction, so that my metric is approximately, my scale factor is approximately exponential. So the metric looks like e to the 2h. The metric looks like this. The scale factor is e to the ht, and then this will be the metric. Okay, now this metric has a symmetry which is rescaling. It has a rescaling symmetry. So if I send x to lambda x, and simultaneously I shift time, so take t to t minus 1 over h log of lambda, then that is a symmetry of the metric. So we would call this isometries, right? Now we are just doing a coordinate transformation, but this is a particular coordinate transformation that does not change the metric at all, which is called isometry. So we have this isometry. So therefore, the result, we expect that the result that we get for the 2-point function should also respect this symmetry. Now, on the other hand, again, if we ignore, so we are neglecting the slow roll correction, neglect epsilon and eta. On the other hand, if we, under the same assumption, if we don't neglect the slow roll corrections, then this phi is just the massless field, right? Or the fluctuations of phi are just the fluctuations of a massless field, because these epsilon and eta are determining the derivatives of the potential. So if the derivatives are 0 or are ignored, then I can forget about the potential or its effect on the fluctuations. And then for a massless field, we know that if K over AH is much less than 1, this is nothing but the ratio of K and the co-moving Hubble, or K times co-moving horizon. If this is much less than 1, which means that if the field is super horizon, then there won't be any time dependence, or the solution will have a constant piece and a decaying piece. But the decaying piece decays extremely fast. So basically, very soon we will just be dominated by the constant piece. So phi k of t is approximately constant up to order epsilon and eta correction. But now if it is constant and if it is supposed to have satisfy this symmetry, if it is constant, then it does not have any time dependence. So therefore the answer should just be a scale invariant. So under this approximation, phi, if we look at it in position, phi of t and x and phi of t and 0, at distances which are large compared to the curvature scale, so that this assumption about being super horizon is valid, this should be x independent. And if we translate that to momentum space, that means that this P of T and K, which we argued is just P of K, there is no T dependence, so we have just P of K, that would be proportional to 1 over KQ. Just because in order to go from the position space to momentum space, I have to do a Fourier transform. So this will be proportional to 1 over KQ. And then I just call the amplitude some constant. So there will be some A over KQ. Of course, in reality, it won't be just KQ. There will be some order epsilon and eta corrections here. I ignore those corrections. And then we can do dimensional analysis to determine that this A should have dimension of mass or 1 over length. And the only dimension full parameter that we have in the problem, relevant dimension full parameter, is the curvature scale. So that would determine this amplitude. So this amplitude is really of order h squared, and then there could be dimensionless quantities like factors of pi and 2, etc. So A should be of order of h squared. So what does it mean? What it means is that the way to think about these fluctuations, this 2-point correlation of phi, is that as our field is rolling down the potential, so if this was V of phi, and we said we have a slow roll solution, then we are writing phi to be a background solution, phi of t and x, so we write phi of t and x to be some phi of t, background solution, plus fluctuations delta phi of t and x. So what we are seeing is that this delta phi, these fluctuations have some non-zero 2-point function at larger scales, at super horizon scales, and those 2-point those fluctuations are scale invariant. The way to think about it is that as the field is rolling down the potential, then it is we said this acts like a clock for us. This field that is rolling down is determining when we want to, where we are in this inflationary solution, and in particular when we want to end the inflation. Now, these fluctuations or this result for the fluctuations tells us that this clock is not very precise. At different points, this clock is fluctuating. Sometimes it jumps up or down of order of Hubble, the curvature scale. And what it implies is that at different points, inflation will end at different times, because now at different points, this fluctuates randomly up and down. So then we will arrive to the bottom of the potential at different times. In particular, something that we can do is that we can do a coordinate transformation, a time diffeomorphism that compensates for these shifts of phi. So we can choose, take t to t plus delta t, such that delta t is equal to minus delta phi divided by phi bar dot. Of course, this delta t is now a function of x. So we are choosing a time hypersurface, which is not fluctuating, so that it compensates for the shifts of phi at different points. So if you want, we can also draw a picture for that. And so if this is the conformal time and this is a space, then we are, this is equivalent to saying that we want to pick hypersurfaces that are fluctuating a bit, so that phi is equal to a constant on every one of these. So here phi of t and x on this hypersurface, this new hypersurface, let me give it even a name. So t tilde equals. Then, for instance, we say here we have phi of t tilde and x. T tilde 1 and x is just phi bar of t tilde 1. So x independent. Here we have phi of t tilde 2 and x to be just phi bar of t tilde 2, and so on. So we are picking hypersurfaces with constant phi. If we do that, then how does the metric look like? The metric will look like this squared equals, well, again, within the same approximation, minus dt squared plus these shifts in time will appear in front of the spatial part of the metric. So here we used to have 2ht, but now we did this time shift. So there will be an extra fluctuating variable sitting here. Where zeta is equal to minus h times delta phi divided by phi bar dot. Now, if we want to estimate the order of magnitude, this is of order of, if we translate what phi dot is in terms of the slow roll parameters, then we will discover that this is of order of h over square root of epsilon times m plot. Okay, so now what is the meaning of this? So we said that we have these fluctuations of the inflaton field that tell us we end inflation at different times at different locations. This is essentially what we had as the definition of the adiabatic fluctuations. Adiabatic fluctuations correspond to identical histories, except that they are shifted with respect to each other at different locations. So that is what these fluctuations in the single field inflation do for us. They produce this the statistical adiabatic fluctuations that just shift the history at different points. So then if we reheat and go into the thermal phase, then we will be automatically in the situation that we described before. At different points in the space, we have just the same thermal history, except that they are shifted in time with respect to each other. So these are static perturbation. And as you see, the amplitude of these adiabatic perturbations are determined in terms of the scale of inflation, the curvature scale of inflation, and the slow roll parameter epsilon. So it's not completely fixed, but what we measure today, or we measure from CMB, that can be translated into a particular value for h over square root of epsilon times m plot, which is a number of order 10 to the minus 5. Okay, so this is everything that I wanted to say today. Let me know if you have questions. Okay, if there is no question, then yeah, I guess then we can stop.